mathematician actually wrote a book on it, Notes on Rubik's Magic Puzzle Cube. It turns out that you can scramble this as long as you want, and as long as you don't break it apart and rearrange it, I can solve it. So, yeah. I'm also prompt. How to actually solve it is to use various patterns that are referred to as algorithms. These algorithms are designed to, well, I shouldn't say designed, to change how you deal with the Rubik's Cube without actually messing up what you've done so far. So what you do is you start by making a cross on the top that connects each of the sides. You then progress to working in each of the corners for that side that you decided to start on. And of course it's not lubricated. That would be far, far too easy. At professional solving tournaments, they take brand new cubes, put petroleum jelly in them and move them 40 times exactly, and then that's what you get to solve. So this next thing you have to do is figure out how to get the the middle sections of the middle part of it, if we want to think of it like that, without, again, messing up what we've done thus far. Like I said, first 2 minutes of this are relatively undramatic. Thank you, Jesse. Actually, no, I wanted to do this. I can show off.
There's a classmate of these children that can do this. He did it for talent show.
They have 3x3s, 4x4s, 5x5s. Some of them are ridiculously large. The funny thing is that the pattern, the formula, once you know the 3x3 and the 4x4, just becomes a more complicated version of that. Because as things go on, all you have to do is move in the new pieces. 2 layers. Of course, the world record for the 7x7 Rubik's Cube is 3 minutes. So anybody want to try that? Yes. Next, you have to match these with this cross that's been made on the top. So those where they go. After I do this, I'll show a few of the more interesting properties. I'm not just going to sit here and solve a Rubik's Cube. And of course, none of them match up, so I get to do this twice. I have to find one that attempts to match its perspective corner. Now, you can all start crying because I'm about to mess it up again, or am I? The problem with this pattern, or should I say the beautiful thing about this pattern, is once you start doing it, people think, he's messing up the cube. No, failboat. So I taught my roommate how to solve this, and he beats my best time by 10 seconds. How's that for payback? No Christian. There we have it.
Yay.
Now, the Rubik's Cube does have a few other patterns other than shiny colors on it. And just to give a few examples of these, the first one I'm going to give is, actually will eventually relate to, you guessed it, Fibonacci numbers.
Aww.
So, by virtue of the fact that any movement on this cube will move another section of the cube, there are certain rules that will always be followed. And as long as you follow some algorithm rules, you can get some pretty interesting patterns going on. For example, switch all the colors around. Put them back, and decide that you don't like the fact that all the centers match up with everything that's around them. So, and by the way, this one I actually did figure out on my own. You just switch the centers. Or, if you want some of the centers solved, but not all of them, you do an algorithm that lets you put 4 of the centers the way they're supposed to be, assuming they would fail, and leaves 2, no I did it wrong. Oh well. Anyway, the patterns on the Rubik's Cube can actually be maintained as long as you follow a few interesting rules. These include always moving whenever you move one axis, you move the one that's on the same side in the same direction. So anytime I do this, I have to do that. Anytime I do this, I have to do that. Anytime I do this, and so on and so forth. I could do this for as long as you please. Despite the fact that the red center's falling out.
Shows use.
Fair enough. Anybody think that looks interesting? I do. So, rather than solve this again, because I don't want to spend 2 more minutes doing that, I'm going to show the part that relates to Fibonacci numbers, and you can start hating on it. Do you recall when I switched it around so that every other part was the opposite sides? So it had a nice little star shape. Well, let's apply numbers to each of those sides. So for the first pair, and we'll assume that up here, we'll have side 1. Down here, we'll have the opposite side. So we've got 1, 3, 5, 7, 9, 11, 13, 15, and 17. Now, if we imagine on this side that any movement over to a non-diagonal counts as a move, then how do we get to the one that's a 10, that's any number plus 10? Anybody see an interesting pattern here?
Oh my gosh.
That was a holy symbol long before it was.
Yes, it was.
No.
2,
Poor Eastern religions lost their symbol for Christ.
14, 16, and 18. Same thing can be done with this one, but I don't think anybody wants to see that again. So what we're going to do is we're going to assume that these are 2 opposite sides on the Rubik's Cube. And we're going to make exactly 2 pairs of moves. We're going to go there and there.
That's an
And a
outside.
number will fall off of the cube and we will magically find nirvana. Now, these 2 bottom rows, the bottom row and the top row, will be rotated all the way around. So these come to this side and these go to that side. Then in the second iteration, we'll do it, but we'll do it with the sides. So that this side goes to that side goes to this side. Well, rather than do this all up here, I'll just do the finished results. 17, 4, 13, 8, 9, 12, 5, 16, 1, 18, 3, 20, 7, 10, 11, 6, 15, 2, and 2. Okay, so if we count moving to another square that's either adjacent or to the perspective square on the other side as a move, notice it takes 1, 2, 3 moves to get to, or 1, 2, 3 moves to get to that perspective number plus 10. On this one, it takes 1, 2, 1, 2, 1, 2. For any of these, we've reduced that to 2. Also, just in the name of maddeningly frustrating different patterns that show up and make you want to smack something, we have here to here is 8. Here to here is 8. Here to here is 16. Here to here is 16. That's true on both of these as well. Now, at first, that doesn't seem particularly impressive because you're following basic rules. But the result is that, again, these match up in the same way as these do. So any pattern that is shown on both of these, we'll mark. 13 to 1, that's 12. 12. 4, 4, 4, 4. Just a shiny little box for you. Now, shall we do the Fibonacci number 1? Personally, when I did this earlier, I wanted to tear the page in half. But not because it's particularly painful, just because I don't like it. You can do a similar pattern with any 2 sets of numbers that are highly related, evens and odds. All the even multiples of 3, all the odd multiples of 3. That one takes a while because you start getting larger numbers up there, but similar patterns emerge. Now let's take our dear friends, the Fibonacci numbers. 1, 2, 3, 5, 8, 13, 21, 34. And for side number 2, we're going to reverse the Fibonacci Fibonacci numbers that show up on side 1. 34, 21, 13, 8, 5, 3, 2, 1, 1. Now, I'm going to actually do this up on the board so that you can see why this is so frustrating. Stage number 2, in which this row is rotated on the cube, and this row is rotated on the cube. For box 1, will give us 13, 21, 34, 3, 5, and 8, and then 1, and 2. This side will give us 2, 1, 1, 8, 5, 3, 34, 21, 13. That's stage 2. Now here's stage 3. Bear in mind that these are each for their respective side of the cube. It switches around. The pattern on this side becomes that. They switch around completely. And it's not maddeningly frustrating, but it's the moment when you look at it and you're like, but these are supposed to not be, these are supposed to be odd. Why isn't that working? All the combinations of Rubik's Cubes, if you take every possible permutation of the cube, just within the bounds of not breaking it apart and rearranging it, would stretch to the sun and back. I think several times, but I don't recall. So what we have here are several different examples of patterns that can be shown with a very obnoxious puzzle. And these patterns, in many ways, relate to numbers in general. Modal addition is actually present on the Rubik's Cube as well, if you think about it, because modal math is more or less when we take an alarm clock, or a clock, you have the numbers 1 through 12, and when you go any higher than 12, you go back to 1. An algorithm on a Rubik's Cube, if you do it enough times, will eventually come back to the position it started. There are even a couple of algorithms that might take you a while because they go through every possible permutation of the cube to get there. Anybody want to do that? So we have certain kinds of modal mathematics. We have an obnoxious series of patterns, and just because I can, it is a platonic solid. And, any questions? Anything at all? And the
How do you
number.
see what color they are?
Hmm?
How do you see what color they are?
I can't.
Yeah, he's
That's green. Also, you have a much simpler way of solving it, but you also have about 12 times as many possible permutations of the cube. And these are 10 to the incredibly large exponent numbers.
Does
So,
breaking it apart count as an algorithm or?
no.
No.
Okay, I was just making sure.
But I mean, it takes me longer to break it apart and put it back together than it does to solve it, because
Yeah.
this, that's easy. Pulling it apart is not.
Yeah.
Fixing a fair share of breakages, I'm sure.